Hello, my name is Joel Keeney, and I will be looking at Van Obel's theorem. To get us started, we will have to see who Van Obel was. We will see how he came to find his theorem and some other theorems that it might be related to. We will also look at a GeoGebra sketch and how we can use GeoGebra to prove Van Obel's theorem or to see the defining characteristics of Van Obel's theorem. And we will also look at some generalizations that are related to some other shapes in accordance with Van Obel's theorem. H. Van Obel was a Belgian mathematician. He was a professor of mathematics in Antwerp. In the year 1820 is when he started his professorship at Antwerp. And his theorem got published in 1878. Van Obel started at the Peter-Newman-Douglas theorem, which states that if isosceles triangles with apex angles of 2k pi over n are erected on the sides of an arbitrary n-gon a sub 0, and if this process is repeated with the n-gon a sub 1 formed by the free apices of the triangle, but with a different value of k, and so on until all values of 1 less than or equal to k less than or equal to n minus 2 have been used in arbitrary order, then a regular n-gon a sub n minus 2 is formed, whose centroid coincides with the centroid of a sub 0. From this theorem, we have a couple of special cases. We have Napoleon's theorem, and then we have Van Obel's theorem, which we will be looking at in further detail. Napoleon's theorem states that if equilateral triangles are constructed on the sides of any triangle, either all outward or all inward, the lines connecting the centers of those equilateral triangles themselves form an equilateral triangle. This would be a special case of the Peter-Newman-Douglas theorem because it is only related to triangles. Van Obel's theorem states that if squares are constructed on the sides of any quadrilateral, then the segments connecting the centers of the squares on opposite sides are perpendicular and of equal length. This is also a special case of the Peter-Newman-Douglas theorem, as it is related to quadrilaterals and the construction of squares on the sidelines of those quadrilaterals. Here we have a couple of links to GeoGebra. These will be posted online and you can click them, or you can just type them into your browser and find them. And we also have a quick screenshot of what Van Obel's theorem looks like in GeoGebra. As you can see, we have our quadrilateral ABCD. We have the squares being formed on the sidelines of those quadrilaterals, and we have our centers of those squares being connected by line segments, and we can see that those are perpendicular to each other. We can also do a little math and see that these lengths, when they are added together, are equal, and that is what Van Obel's theorem states. Here we have our GeoGebra tool for Van Obel. With this tool, it will construct the squares on the sidelines of our quadrilateral, and it will also construct our line segments. Under the wrench, we have a little tool called Van Obel. With that, we will construct our 4 points of A, B, C, and D. Once we plot that 4th point of D, our squares on the sidelines will show up. Our line segments connecting the centers of those squares will show up, and values for the distance of those line segments will show up. We can also see that those line segments are perpendicular to each other. We can see that our values are equal to each other. And we can also see that if we move any of these 4 points, then the perpendicular will always be there. We can see that our values are always equal to each other, our distance values. And we can see that it works for convex, concave, and crossed quadrilaterals. The only thing that we may have to do to see that it works 100% is extend those line segments past center so that we can see where they intersect with each other. The only reason why I do not have it doing that is so that I can show you the values of the distance and how they are always equal to each other. Here we have a generalization of Van Obel's theorem as it relates to rectangles. This was discovered or proven around 1994, over 100 years after the original Van Obel's theorem was published in 1878. This theorem states that if similar rectangles with centers E, F, G, and H are erected externally on the sides of quadrilateral ABCD as shown, then the measure of angle FOG would equal 90 degrees, and the ratio of EG to FH would equal the ratio of XA to AB. Further, if J, K, L, and M are the midpoints of the dashed segments shown, then the distance of KM would equal the distance of JL, and the angle of JL and KM would equal the angle of the diagonals of the rectangle. Here is a picture to help you understand what we stated in this generalization of Van Obel's theorem. We can see that the measure of angle FOG is 90 degrees, and we can see those ratios are similar. We can see those dashed segments, the distances are equal, and we can see those other angles are equal to the angles of the rectangles. Here we have another generalization of Van Obel's theorem as it relates to rhombi. This was also discovered or proven around 1994, about the same time as the rectangles. And it states that if similar rhombi with centers E, F, G, and H are erected externally on the sides of quadrilateral ABCD as shown, then the distance of EG equals the distance of FH, and the measure of angle FWG equals the measure of angle ABY. Further, if J, K, L, and M are the midpoints of the dashed segments shown, then the ratio of KM to JL would equal the ratio of YA to XB, and the angle of JL and KM would equal the angle of the diagonals of the rhombi. Once again, here's a picture for us to see what we are stating in that generalization. We can see that those distances are equal, EG and FH are equal to each other. We can see that the measure of those angles are equal. We can compare those ratios and see that those are equal, and we can see the angles of JL and KM equal the angle of the diagonals of the rhombi. Here is the last generalization that I am going to show you today. It is about parallelograms. This was discovered a couple years after the rectangles and rhombis, or discovered or proven, I should say. And it states that if similar parallelograms with centers E, F, G, and H are erected externally on the sides of quadrilateral ABCD as shown, then the ratio of FH to EG would equal the ratio of XY to YB, and the angle of EG and FH equals the angle of the sides of the parallelograms. Further, if J, K, L, and M are the midpoints of the dashed segments shown, then the ratio of KM to JL would equal the ratio of YA to XB, and the angle of JL and KM equals the angle of the diagonals of the parallelograms. Another picture to help us see what we stated in that generalization, and we can compare those ratios, see that they are equal. We can compare those angles and see that they are equal. And that is what I have on parallelograms. Here are my references that I use to help me explore into Van Aubel's theorem and how it can be used and what it shows. And I hope you enjoyed my presentation about Van Aubel's theorem.